Hi, this is Wouter. I am presenting the paper Variational Message Passing for Online Polynomial NARMAX Identification at the American Control Conference 2022. So this is about system identification with NARMAX models. NARMAX stands for nonlinear autoregressive moving average with exogenous input. It's an important model class for SysID, and an example is, for instance, robot arm control, but there's a textbook reference for more examples. I'm focusing on the subclass of polynomial models. How that works is that we've got a current input UK, previous inputs, previous outputs, and previous noise instances, and we are regressing those on the current output using polynomial regression with coefficients theta and a polynomial base expansion function pi. The current noise instance, or actually all noise instances, follow a zero mean Gaussian distribution with precision parameter tau. I'm going to estimate parameters in this model using Bayesian inference. Now you might ask, what is Bayesian inference? It's about updating the belief over an unknown variable in a model given data. So I've got an animated example here. On the left you'll see a random walk with Gaussian distributed increments with some unknown precision parameter, and on the right you'll see first of all, an uninformative prior for tau, precision parameter, it's flat. We have no a priori knowledge that any value of tau is more likely than others. And what you're going to see is that as data streams in, this distribution is going to concentrate on this true value of tau. Why Bayesian inference? Well, point estimators, such as least squares and maximum likelihood, overfit when sample sizes are low. Overfitting means that you fit to noise in your training data, which is not going to be there at test time, so your predictions are off. And overfitting is especially bad in system identification when you want to simulate for a large time horizon, because you want to make predictions far into the future. Bayesian inference is naturally robust to overfitting. So in one sentence, the use of probability distributions has this naturally regularizing effect that it avoids those noisy samples because they're deemed unlikely. You might wonder, why isn't Bayesian inference used everywhere? Well, it's simply computationally expensive to run the inference algorithm. Monte Carlo sampling, if you've heard of that, is a very well-known approach, and it's just very expensive because you have to do a lot of computations to sample and approximate this posterior distribution. So for the last 2 decades, people have been working on a different approximation technique called variational Bayes. You might have heard of this from variational autoencoders, but it's a general technique. And today I'm going to talk about a variational Bayesian estimator that's distributed over a factor graph that represents an efficient inference algorithm. So to do Bayesian inference in a NARMAX model, we first have to cast it into probabilistic form. So if you absorb this noise instance EK, then you can cast the entire dynamics as a Gaussian likelihood function. These bold symbols on the left are just the vectors of delayed inputs, outputs, and noises, and this phi of k is just shorthand for the polynomial expansion based applied at time k. So it's just quite a simple Gaussian likelihood. The coefficient theta and tau, the noise precision, are unknown, which means we have to put prior distributions on them. For the coefficients, I'm going to use a Gaussian, and for the noise precision parameter, I'm going to use a Koudahl distribution. So if you have priors and a likelihood, then you can map all of this to a factor graph. This is Forney-style factor graph. We've got observations, YK, UK, and the delayed vectors. Then everything in this dotted box, those are all the operations involved in this NARMAX likelihood function. And these two terminal nodes on the left are the initial priors, but you should read this graph as everything between those series of 3 dots is applied recursively at every time step. And the prior at k is the posterior at k minus 1. These two nodes, the ones marked with an equality, they are where we apply Bayes rule to get posteriors. So how does that work? These are called the Bayesian filtering equations, and we derive a recursive expression in the paper. initially at k equals 1, we've got this very simple application of Bayes' rule. If you read it right to left, we've got two initial priors. We've got a quite simple likelihood function of just some output given some input. And we've got an evidence term that has only the observed variables, and that gives us our first posterior distribution. In the next time step, we see the first appearance of this previous noise instance. So at k is 2, we've got E1 in the likelihood function. And what you might have also noticed is that we have used the posterior that we have derived in at k is 1. We are now using that as the prior at k is 2. And outside of that, we still got the same structure here. We've got a set of priors, then a likelihood, then 1 over the evidence, and that's going to give us a posterior distribution. So at k is larger than 2, by induction, we can use the same structure over and over again. We've got some previous posterior, then we've got a new data coming in, and that's added through this correction factor with the likelihood over the evidence. That's going to update our posterior to this new set. However, these are the true posterior distributions. We cannot compute these because the evidence terms involve a marginalization over the unknown random variables, and that's intractable. So we resort to variational Bayes. That means we form a free energy objective function with respect to recognition model Q, and it looks like this, but you can actually decompose this energy function into more easily computable terms. The details are all in the paper. And so this recognition model Q, what does that look like? Well, it factorizes into two marginal recognition factors, one for the coefficients, which is parameterized to be a Gaussian, and one for the precision parameter, which is parameterized to be a gamma distribution. Now we get the update equations. We can actually derive optimal forms of the marginal recognition factors. For coefficients, they look like this. It's some exponentiation over a sum of expected values. And for the precision parameter, we see exactly the same structure. But you might notice that they are coupled. So the optimal form of theta depends on tau, and the optimal form of tau depends on theta. And what this means is that you initialize these recognition factors, usually based on the previous state, or the recognition factors at the previous time point. And then you iterate these update equations until convergence. Now, this is exactly what it descends, and this is a fairly simple model. So it usually takes 2, maybe 3 iterations to reach convergence. How do you actually compute all of this efficiently? Well, we can map terms of these update equations to specific locations in the factor graph, and that means that we are doing variational message passing. So it looks like this. Here we've highlighted 4 messages, 1, 2, 3, and 4. 1 and 3 are the recognition factors from the previous time point. They represent the priors. And 2 and 4 are the contributions of the new data coming in, and they form also again Gaussian gamma distributed messages. And the prior and the likelihood terms are combined at the equality nodes through Bayesian inference to update the marginal recognition factor, which is, as you remember, the approximation of the posterior. And these updates are actually just summations, so that's fairly straightforward. So the whole point of system identification is that once we have all these parameters, we can put in some input and then we can simulate an output. And what we have is that this output is unobserved, and which means that we can treat it as a random variable and use Bayesian inference to infer a probability distribution to characterize this future output or this unobserved output. And we call that a posterior predictive distribution, and that looks like this. It's essentially approximately Gaussian. We have some mean and some covariance around that, and mu t, lambda t, alpha t, and beta t are just the final variational parameters of the recognition factors at some k is equal to t. Now, what does it look like? I've got a small simulation here, simulation experiment here. The left column has training data, inputs and outputs, and they are streaming in. In the middle column, we've got a validation data set. So there's some input which isn't shown and some validation output that's unknown, shown here. The model has to do generate simulations for this validation data set at every time point. So as training data streams in, it has to do one simulation every time point. And what you're going to see is that I'm comparing the variational message passing based method with recursive least squares. What you're going to see is that VMP generates an sensible simulation earlier on. It also recognizes that these peaks in the validation data set are problematic. It has a wide uncertainty band around that, and is going to focus on minimizing its prediction error for those regions. And on the right column, you'll see simulation errors, so the difference between the actual validation output and the predicted validation output, the simulated validation output. And you'll see the VMP method generating smaller results earlier on, smaller values earlier on. So VMP has these wide uncertainty bands for the peaks around here, and only now does RLS actually produce something sensible. And you can see the VMP is already, RLS is still struggling with these peaks, but VMP is doing that sort of thing. Yep. Now, if you repeat this as a verification experiment, you do 100 Monte Carlo runs of this for some polynomial order, delays 1, the details are on the paper. What you see is that the Bayesian estimator dips under both the online least squares estimator and also an offline least squares estimator technique ILS. But specifically for smaller sample size regimes. At some point, they have more than enough data to all of them have converged essentially on the true parameters. So in conclusion, variational Bayes outperforms least squares in small sample size regimes. We did not use informative priors, and I argue that variational message passing is an efficient inference algorithm. And basically my argument is that at 2 iterations, the computational complexity is just 4 times that of recursive least squares, which is still blindingly fast. That's it. These are my collaborators, Albert, Magnus, and Maarten. And I'm going to answer questions at the conference itself. Thanks for listening.